Hi, welcome to this video about a phenomenon which is called encoder-wraparound and how we can solve this. Well, let's start with the basic model of a feedback system. P is my process, my plant, my system to be controlled. And in this case, it's a position control system, so my output is a position. Could be a rotational position or, for instance, a translational position. So my reference R is also a position. It's my set point, it's a position set point. And the difference of R and C is my error, to which my controller HR is going to react on. And in this example, the output of my controller is equal to a voltage with this, which is the input for my process P. The output of P, my position, is mostly measured by means of an incremental encoder. So my incremental encoder yields a number of pulses. So we have to count the number of pulses to get a measure for the position of my process. So we need a counter mostly provided on my control board, so my control board or my microcomputer board, whatever. So we need that counter to count these pulses. Let's look to a more detailed model. In this example, we have an output of my system, which is a speed, a rotational speed, and rotations per second. When we want to measure the position, we have to we have to integrate that speed, so we get the position. And when we want to model that encoder, we have to multiply these rotations with the number of encoder pulses per revolution, in this example 1000. And when we have two channels, so an incremental encoder with a quadrature operation, then we can count every edge of these two encoder channels, so we can multiply the number of encoder pulses by 4. So this is more or less a model of my encoder. But in reality, we have to use that counter, and that counter has a maximum value to which my counter can count. So when I have one pulse more than my maximum value, my counter starts to wrap. It goes from its maximum value down to 0 again. But that is not in fact what is happening, because the number of pulses is increasing in reality, but my counter says, well, after one pulse more than the maximum value, I go back to 0 again. But let's see what happens in that situation. This is my set point, my position set point, which keeps on increasing, for instance. But at a certain point, my counter starts to wrap, so it goes from its maximum value to 0. So in that case, we get a huge error over here. My PID type of controller starts to react on it, sends out its maximum voltage to the motor, and we get a lot of problems in my control system. So we have to solve this. Well, how we can do it, I'm going to illustrate that by means of this example, in which we have a roller over here from the paper industry, and that roller transports paper, and it's driven by a motor with a transmission over here. And this drawing, the encoder is on the motor shaft, but in my example, there could be an encoder on this roller. Well, let's say this encoder gives us 10,000 of pulses per revolution of this roller. Let's say this roller has a diameter of 50 millimeters, and the encoder is connected to a 16-bit counter. But my microcomputer to which this counter is connected has an internal bus of 32 bits. So what we are going to do is we are going to look at what value my counter starts to wrap and how we can solve this. Let's start with some basic mathematical operations. My counter starts to wrap every 2 to the power 16 bits, because it's a 16-bit counter. So my maximum value is 2 to the power 16 minus 1 counts, which equals 65,535 counts. Well, every roller revolution equals P times D meters, which is P times the diameter of my roller, which is equal to 0.157 meter. So now we can calculate after how many meters my counter starts to wrap, and that is equal to that value of 35,535 divided by 10,000 pulses per revolutions, which gives me the number of revolutions multiplied with that 0.157, which equals somewhat more than 1 meter. So after 1 meter of paper transport in this example, my encoder starts to wrap. So it goes from that maximum value over here to 0 again. But my reference, the set point to my controller, keeps on increasing because my roller keeps on moving. So the error suddenly goes from a high value up to down to 0, and the controller starts to react on that and puts its maximum voltage on the motor, and we get a lot of problems. So we have to detect that wraparound, and we have to correct for that wraparound. So this is what my original counter signal is doing. It goes at a maximum value, and one count later it wraps from the maximum value down to 0 again. So the solution is that we first of all detect that wraparound. So we can say, well, when we have an increasing counter value, we can see when the counter value, for instance, decreases to half the counter value it could have. And then we say, well, this should be a wraparound. So now we know the counter wraps. So now we have to correct that signal over here, which is the sawtooth signal, which we can see over here. So after that detected wrap, we add the maximum value of the counter towards this signal, multiplied by the times of the number of wraps we already had, and we add that to the actual counter value, and then we get a corrected signal which looks like the dashed line over here. And we can do that because the internal data bus has a width of 32 bits, so the signal ranges from when we have a bidirectional operation, it ranges from minus 2 to the power of 31 up to 2 to the power of 31 minus 1. So we can do that. We can measure the number of reps, and we can correct that signal. And remember, we can correct it 2 to the power 16 times. So we can correct that signal of 1.03 meters 2 to the point 16 times, which was 65,000 times. So then we have a really huge area in which this control system can function without any problems. So that is what we are going to do, and that is what we have seen here in theory. So now let's look to a MATLAB demo in which I'm going to illustrate that by using MATLAB and Simulink. Well, I'm going to a Simulink model over here, in which this is my wrap, my counter value, which is going to wrap. And here I have some MATLAB code which is going to detect that and which is going to correct that. Well, let's have a look how the code looks like. And we see over here that what we are doing is when we measure a wraparound, then we add up to the encoder value the number of reps multiplied with the maximum counter value over here. And we add up the number of reps, we add that by 1. And of course, when we transport in the opposite direction, we decrease the encoder value with that maximum value multiplied with the number of reps. And when we don't detect a rep, then we keep on counting, which is illustrated over here. So that is my simulation. So how does it look like in practice? Well, let's look to the scope over here, in which my upper plot is my uncorrected signal from my counter over here. And we see the sawtooth behavior of that signal. And here we see that my corrected signal, which is the output of my MATLAB code, which really detects at a very good, at the right point, the number of reps and corrects that using the procedure which we discussed a couple of seconds ago. So summarized, when you have a position control signal, always keep in mind that your counter wraps up at any time. You should calculate whether or not this is a problem, and when it is a problem, we have shown you an example how you can correct that. Well, that's all about anti-encoder wrap up. So thank you very much for watching this video, and I see you next time.